In this video, we're going to talk about how to calculate the lateral area of pyramids and cones. Now, we were exposed to this phrase previously, lateral area, and this refers to the area of everything that is not the base of the figure. And that was true for prisms and cylinders. That'll be true for pyramids and cones as well. So you've been given a pyramid and a cone. And what is given below are what are referred to as two-dimensional nets of the shapes. And so this is what it would look like if you took each of the figures and you broke them down into 2 dimensions. You could imagine cutting the nets out of paper and folding them up in order to make the 3-dimensional shape. For the pyramid, we've been given the length of the base, and this is a square pyramid as given in the problem, and we've been given the lateral height, or sometimes that was referred to as the slant height. And if we go down to our net, we can see that we have the square base here, and then it's made up of 4 triangles, 1 for each side of the base, and the lateral height is the height of that triangle. Well, we can calculate the area of that triangle. The area is equal to 1/2 times the base of the triangle, which is S, times the height of that triangle, which is L. And according to our figure above, that's going to give us an area of 1/2 times 4 times 5, or an area of 10. Since there are 4 of them, 4 triangles, we're going to multiply by 4. So 4 times the area of one of the triangles would be 40. And this is what we're going to refer to as our lateral area. Now, if I was to write out that lateral area formula for this figure, we would do 4 times 1/2 SL. Okay, and I'm using S and L, or we could have used B instead of S for the square. But one thing I want to make sure we recognize is if I rearrange this formula, I could rearrange it as 1/2 times 4S times L. And we might ask ourselves, well, what is this 4S? Well, it is 4 times this length right here. And for the base of this figure, that calculates the perimeter of the base. And this is not a coincidence. This will always happen. The length of that base times the number of sides is always going to give you the perimeter of that base. And so this provides us a better way to calculate lateral area that will work for all figures. 1/2 times the perimeter times the slant height. And by perimeter, we mean the perimeter of the base. So let's take a look at the cone. Now the cone, when you represent it as a net, it has a circular base. So that's here, our base. And then it has a sector. And if we want to know the lateral area of this figure, we want to know the area of this sector. Now, when we studied circles, we learned that the area of a sector can be calculated using the following proportion. The measure of the angle over 360, or we could use 2 pi if we were going to work with the radians, is equal to the area of the sector divided by the area of the circle. And by the area of the circle, we mean the area of the larger circle that the sector is a part of. Now, what's slightly problematic about this question is we are not given the angle measurement here. And so it's going to be difficult for us to figure out the measure of the angle over 360. And we could calculate that angle measurement. The way we would do it is we would also remember that this ratio is equal to the length of the sector divided by the circumference of the circle. So let's go about finding those values here. The length of our sector is this segment right here. And the length of our sector is going to be equal to the circumference of the base. We saw something similar with cylinders where the circumference of the base represented how wide the lateral surface was, but the lateral surface in that context was a rectangle. Here we've got a sector. But the circumference of the base is going to be equal to 2 pi r, or in the context of our problem where r is 5, it's going to be equal to 10 pi. So that is the length of our sector. Okay. So then the question is, well, what is the circumference of the entire circle? Well, the circumference is going to be equal to 2 pi times the radius of the bigger circle, and the radius of the bigger circle is given by this length here in the sector, which has been labeled for us as being equal to the lateral height or slant height of the cone, so 2 pi L. In the context of our problem, circumference is equal to 20 times 2 pi, 40 pi. So this conclusion tells us that the length of our circle divided by the circumference is equal to 10 pi over 40 pi, or a ratio of 1 to 4. That's going to allow us to calculate that this angle measurement must be exactly 1/4 of the circle, or 90 degrees. And that's going to allow us to calculate the area of our sector. Now we again know that L is equal to 20, so let's go ahead and find the area of the big dotted line blue circle. The area of that is going to be pi times 20 squared, or 400 pi. And the area of our sector then is going to be area over 400 pi is equal to 90 degrees over 360, or 1/4 of the circle. And you can solve that by cross multiplying, or just recognizing that an area of 100 pi is exactly 1/4 of an area of 400 pi. Now, it might be nice if we could simplify this a little bit and come up with some kind of formula so that we don't have to do all of these calculations every single time. So let's try and follow the same process using variables instead of plugging in our numbers. So we said that the circumference of the base was 10 pi. And that 10 pi also represents the length of our sector. And then we said and that was calculated by using 2 pi r, right? We were going to keep it with variables. And then we said that the circumference of the entire circle that the sector is a part of is equal to 2 pi L. And we said that that would be equal to the area of the sector divided by the area of the whole circle. And the area of the whole circle was pi times 20 squared. We calculated that here, or I could write that as pi L squared, since we've decided that L is the length of our radius. And the area of the sector is what we're looking for. So let's try and get it by itself. So we're going to multiply both sides of this by pi times L squared. And that's going to cancel out the pi L squared on the left. So the area of our sector is equal to what we get when we multiply these two things. Now, the pi here on the top and the bottom, we can cancel those out. They simplify to 1. Same with the 2 and the 2. And one of these L's is going to cancel out that L on the bottom of that fraction. And we'll remember, we can simplify fractions like this whenever we're multiplying. If you're more comfortable multiplying numerator and denominator first, then simplifying, we'll come to the same conclusion. But notice what is left over. We've got a pi that's left over. We've got an r that is left over. And we've got an L that is left over. And we are left with a very straightforward and easy to use formula for finding the area of that sector. And let's just see how that agrees with our answer of 100 pi. We were told in our original problem that r is equal to 5 and L is equal to 20. And so if we wanted to calculate the area of the sector being that curved surface that makes up the lateral area of the cone, we would do pi times radius times lateral height, which is 100 pi, which agrees with the answer we got when we did it the long method. And the area of the sector represents the lateral area, and so that can be a formula for lateral area for a cone. So we have our two formulas here, so let's just record them. The lateral area of a pyramid we learned is going to be equal to 1/2 times the perimeter of the base times the lateral height. And the lateral area of a cone is pi times the radius of the base times the lateral height. And we'll remember the difference between lateral area and surface area is that surface area also includes the bases. In this case, since we're doing pyramids and cones, there's only going to be one base that we need to include. For the square pyramid, we would add in the area of the square, and for the cone, we would add in the area of the circular base.